Welcome to the Deep Dive, where we plunge into the cutting edge of research to bring you the most vital insights. Today, we're exploring an arena you interact with constantly, perhaps without even realizing it. We're talking about the invisible forces powering our modern world, particularly, the rapid growth of AI and smart devices. Just imagine a world where your smart speaker anticipates your needs, self-driving cars navigate flawlessly, and, well, countless intelligent gadgets enrich your home and work. This isn't just a vision, it's a rapidly accelerating reality. And this relentless march of technological progress, it's pushing our conventional computing systems to their absolute limits. We're talking about a demand so intense, it's forcing us to rethink the very foundations of how we build computers, especially at the edge of our networks.
It's fascinating, actually, because for decades, Moore's Law has been our guiding star, right?
Yeah.
Driving incredible advancements. We've been constantly shrinking transistors, packing more onto a chip, boosting performance exponentially. It's been amazing. But now we're encountering very real physical boundaries and architectural bottlenecks, too. These aren't just minor hurdles. They necessitate fundamentally new approaches. The traditional way we've built computers, based on CMOS technology and the classic von Neumann architecture, it's genuinely starting to show its age, particularly when you pit it against the intense parallel processing demands of modern AI and this burgeoning field of edge computing, where devices need intelligence on-site, not just relying on the cloud.
Right. And this is exactly where our source material for today unveils something truly groundbreaking. It details a hybrid architecture, one designed not just to cope with these looming limits, but to brilliantly transform some traditional problems in chip design into powerful advantages. This innovative system, it aims to create a seamless fusion, blending the reliability and, the scalability of existing CMOS technology with the novel capabilities of these emerging two-dimensional or 2D materials-based memristors. It's kind of like combining a finely tuned, trusted engine with a revolutionary new type of fuel. So our mission in this deep dive is to extract the most important nuggets of knowledge from this fascinating research article. We want to help you understand this innovative approach, grasp why it's so desperately needed right now, and appreciate its profound implications for the future of computing, especially for the smart, responsive world we're increasingly living in. So let's jump right in. Okay, so for as long as many of us have been using computers, the story has largely been one of continuous improvement, driven by making transistors smaller, packing more onto a chip. This constant, almost magical scaling of CMOS technology. It's been absolutely revolutionary. It underpins every technological leap we've witnessed, really, from bulky desktops to the smartphones in our pockets. But like any physical boundary in engineering, there's a point where it becomes incredibly challenging, astronomically expensive even, and eventually maybe even counterproductive to shrink things further. Our sources make it abundantly clear: the relentless pursuit of improved performance, greater data throughput, higher integration density. It's pushed CMOS scaling to its absolute physical and economic limits. We are undeniably hitting a fundamental wall.
Precisely. And this wall isn't just about size, it's about architecture too. The existing hardware designs, particularly those built on traditional CMOS and the classic von Neumann architecture, they struggle immensely, especially with the massive parallelism and, crucially, the energy efficiency required by modern machine learning and AI algorithms. Think about it. The von Neumann architecture famously separates the processing unit, the CPU, from memory.
Right.
So data constantly has to shuffle back and forth between them. It's like a chef repeatedly running to the pantry for every single ingredient. It's just not efficient. This creates a significant memory bottleneck and constant communication issues, often referred to as the von Neumann bottleneck. And it dramatically hinders performance and wastes a ton of energy. It's simply not built for the way AI thinks,
Not at all.
And the challenge becomes even more acute when we talk about AI algorithms running on edge devices. These aren't powerful data centers. They're the smart sensors in your car, the cameras on a drone, maybe the tiny processors in your wearable tech, or even your smart doorbell.
Things that need to be small and low power.
Exactly. For these devices, the demands are incredibly specific and unforgiving. We're talking about crucial issues like privacy. You don't want sensitive data constantly leaving the device, right?
Definitely not.
Then there's ensuring robust security, keeping manufacturing costs down for mass adoption, minimizing latency for real-time responses. Think of a self-driving car needing instantaneous reactions.
Can't have a lag there.
No way. And managing severely limited bandwidth when a device can't just constantly ping the cloud. All of these factors demand computing architectures that are not only highly energy efficient, but also massively parallel, with incredibly low latency and minimal memory requirements built right in. Traditional CMOS, designed for a different era of computing, it just isn't cutting it for this new frontier.
That's a really powerful way to put it, not cutting it. And a huge part of that bottleneck, as you mentioned, it comes down to memory itself. When you think about the RAM in your laptop or the flash storage in your phone, you're essentially talking about storing information as electrical charges. These conventional memory technologies, they rely on trapping or moving electrons to represent bits of data, zeros and ones. It's a method that has served us incredibly well for decades, no doubt. But as devices continue to shrink, and we push towards those ever lower technology nodes, meaning smaller and smaller transistors, this charge-based storage method, well, it starts to run into significant physical problems. You get issues like charge leakage, signal interference, fundamental limits to how much charge you can reliably store in a tiny, confined space.
Yeah, absolutely.
These aren't minor glitches. They impact the very reliability, speed, and energy efficiency of the entire system. It feels like we're trying to fit an elephant into a teacup, almost.
And that raises a profoundly important question. What if memory could also do some of the processing? You've precisely hit on the core issue there. The degradation in performance, reliability, and noise margin that traditional charge-based memories suffer at these lower technology nodes. It's a major, unavoidable concern. So, to truly overcome the von Neumann bottleneck, a really promising paradigm shift is in-memory computing.
In-memory computing, okay.
This isn't just a buzzword, it's a fundamental architectural change. The idea is that data is processed directly within the memory units themselves, drastically reducing or maybe even eliminating the need to shuttle data back and forth.
So avoiding that trip to the pantry altogether.
Pretty much. This approach exploits physical principles like resistive switching, or RS moving entirely beyond the charge storage paradigm. Emerging memory devices are actively exploring this in-situ processing. It's a fundamental shift aiming to bypass these severe limitations and unlock new levels of efficiency for AI workloads, especially at the edge.
Okay, so resistive switching, in-memory computing. If we're hitting these fundamental walls with traditional silicon and charge-based memory, what's the exciting, revolutionary alternative that our sources point to? This research introduces us to a truly fascinating component called a Memristor. It's a cool name, a device whose name perfectly describes its function, a memory resistor. It's a unique electronic component that can literally remember its past electrical history, changing its resistance based on the current that has previously flowed through it, and then crucially, retaining that resistance state even when the power is turned off. Non-volatile.
That's the key.
This non-volatility, combined with its ability to hold multiple resistance states, makes it an ideal candidate for this in-memory computing idea, right? Fundamentally changing how we store and process information. It's almost like giving memory a rudimentary form of intelligence.
Indeed, the concept of a memristor is powerful, but the real innovation often lies in the materials science behind it. While we've seen significant progress with traditional transition metal oxide-based resistive RAM, TMO-RAM, people call it, which is actually nearing commercialization, the past few years have witnessed a surge of experimental demonstrations of 2D material-based RRAM, two-dimensional materials.
Like graphene. Or other ones.
Exactly like graphene, but in this case, other materials are showing even more promise for memory. And what's truly compelling is why these 2D RRAMs offer such significant advantages. They can overcome the vertical scaling limits that TMO RAMs face. They've literally demonstrated impressive resistive switching at the monolayer level.
A single atomic layer. That's incredible.
It is. An incredible feat of miniaturization. Furthermore, the fundamental mechanism of resistive switching in 2D RM appears to be entirely different from its TMO counterparts. This distinct physical principle strongly suggests it may dramatically outperform TMO RAM in terms of operating speed and power consumption. But here's where it gets particularly exciting for this deep dive. A specific finding highlighted in our source is that 2D ARMs can achieve state currents spanning multiple orders of magnitude, from sub-nanoampere all the way up to milliampere.
Wow, that's a huge range.
A vast dynamic range. This ability to switch between such widely different resistance levels, it's a capability not yet reported for TMO RAMs. Think of it like a dimmer switch with an almost infinite number of settings compared to one with just a few clicks, you know?
Okay, yeah.
This broad dynamic range is absolutely crucial for advanced analog computing applications, especially for creating nuanced multi-state synapses in artificial neural networks, where subtle gradations in signal strength are key to learning and performance.
That level of control and flexibility sounds amazing. So with this immense potential of 2D materials, the specific choice of material becomes paramount, I imagine. This research zooms in on multi-layer hexagonal boron nitride, or HBN, for their memristors. Why this particular material? What makes HBN so critical to enabling this specific breakthrough rather than, say, graphene or something else?
Yeah, HBN is a genuine game changer here for several compelling reasons. It offers a perfect blend of manufacturability and performance. Firstly, and crucially for any real-world application, these HBN memristors can be fabricated using scalable chemical vapor deposition, or CVD, methods.
Scalable. That's key.
Absolutely key. This means we can produce them efficiently on a large scale, facilitating wafer-level integration, which is essential for eventual commercial adoption and making these chips affordable. It's not just a lab curiosity, it's built with mass production in mind from the get-go. Secondly, a key finding is their exceptional reliability. They exhibit analog bipolar resistive switching in over 96% of devices.
Over 96%. That's very high.
Incredibly high yield. And the analog nature of their switching makes them exquisitely suited for multi-state memory applications, particularly for simulating those continuous adaptive connections in neural networks, and for the stringent demands of edge computing, where fine-grained control is far more efficient than simple on-off digital states. But here's where HBN truly pulls ahead. These devices demonstrate more than 26 stable conductance states.
26?
Wow. Yeah. To put that in perspective, achieving this many reliable, distinct memory states is a formidable challenge with standard TMO memristors, which typically offer far fewer, maybe just a handful. This expanded palette of states allows for significantly richer information storage and processing within a single device, meaning a single memristor can hold much more nuanced information.
Okay.
More states, more information density. Exactly. Finally, and perhaps most elegantly, HBN memristors offer superior control over what's called the potentiation process. This is essentially how you precisely adjust or fine-tune the memory states, akin to strengthening or weakening a synapse in a biological brain. Compared to traditional metal oxides, HBN devices show a much smoother and more predictable trend, even when operating in the extremely low-power sub-microampere regime.
Smoother control, even at low power.
Yes, and this superior control is attributed to a fascinating microscopic detail: the ionic migration responsible for the resistance change. It occurs within native defects that are only a few atoms wide, nestled within a highly stable crystalline HBN lattice. This structure prevents the lateral propagation of these ionic movements.
Ah, so the changes stay very localized.
Precisely. The adjustments stay incredibly localized and precise. Think of it like trying to draw a very fine line with a perfectly sharpened pencil versus a blunt crayon. This confined, precise movement leads to much more accurate and reliable memory adjustment, which is indispensable for the iterative learning processes of AI.
That level of precision and stability, combined with the multiple states, it paints a picture of a truly sophisticated memory element. So when you bring all of this together, the reliable, scalable CMOS and these cutting-edge HBN memristors, what does this all mean for the big picture? The core idea, as you mentioned, is to create a seamless fusion. It sounds like they're not just bolting two different technologies together, they're actually designing them to coexist and leverage each other's strengths in a really unprecedented way. It's almost like building a brain where one part is fantastic at initial sensory processing and another excels at memory and adaptive learning. Is that a fair analogy?
That's a perfect analogy, actually. You've captured the essence beautifully. This is truly a best of both worlds scenario, meticulously engineered to push beyond current limitations. The proposed hybrid architectural framework consists of two main yet distinct components: a CMOS encoder chip integrated with a 2D HBN memristor crossbar array acting as a decoder chip. This specific pairing is ingeniously designed for extreme learning machine, or ELM, algorithms. Yeah, ELMs are particularly well-suited for the rapid, real-time demands of edge computing. They learn very quickly. But what's absolutely brilliant and innovative about the system is how it actively utilizes the inherent nonlinearity and even device mismatch found within conventional CMOS circuits.
Wait, mismatch, isn't that usually a bad thing designers trying to get rid of?
Exactly. These are qualities that designers typically spend immense effort and expense trying to eliminate or compensate for. Here, they're not seen as challenges, they're turned into advantages. They're leveraged for creating an incredibly efficient design with a minimum transistor count. This unique philosophical approach aims to transcend current technological limitations, offering not just incremental improvements, but significant foundational advancements in overall system performance, especially for energy-constrained AI.
That is fascinating. Taking something usually seen as a flaw, a bug, and turning it into a feature. It speaks to a very clever design philosophy. Now, we have a clear understanding of the what's and the why, but to truly appreciate this innovation, we need to understand the how.
Mm.
So let's peel back another layer. How do these two seemingly different technologies, the familiar CMOS and these novel Memristors, actually work together in practice? Our sources lay out a clear, step-by-step process for this hybrid architecture. It's much more than just slapping two chips together, isn't it?
Absolutely not. It's a deeply integrated and elegant solution. At its core, this system employs a local receptive fields-based extreme learning machine, or LRF-ELM algorithm.
LRF-ELM. Okay, break that down a bit.
Right, so an ELM, as I said, is a type of neural network that learns incredibly fast. The local receptive fields part means that instead of every input connecting to every hidden node, they connect to specific localized regions, kind of like how our visual cortex processes parts of an image separately first.
Makes sense.
What's particularly clever about this LRF-ELM variant is that the weights, the strength of connections between the input and hidden layers, are local, random, and critically fixed.
Fixed and random. How does that work?
We'll get to that. But
Yeah.
the point is, they don't need to be extensively trained or stored separately, which saves immense power and memory. Only the output weights, those connecting the hidden layer to the final output, need to be learned and adapted. And the beauty of the overall system architecture lies in the fact that while the CMOS encoder and Memristor decoder chips work in tandem, they are electrically isolated.
Isolated. Why is that important?
It's a masterstroke, really. This isolation allows for separate optimization of each component. You can maximize their individual strengths without compromise, and it offers incredible flexibility for future upgrades.
Okay, that modularity and targeted optimization make perfect sense. So let's zoom in on that CMOS encoder chip first. This is the intelligent front end, correct? It acts as the initial processing unit, handling the raw input data and intelligently preparing it for the Memristor array. What exactly is this complex chip doing in the overall system?
Yes. The CMOS encoder chip is the system's brainy front end. It's responsible for forming the input and hidden layers of that LRF-ELM network we just talked about. Within this chip, a key, highly optimized component is the 9D Gaussian cells,
Oh.
9-dimensional.
9D Gaussian cells. Sounds complex.
It is, but it's efficient.
Mhm.
These cells serve as the hidden nodes of the network, and they are ingeniously implemented using subthreshold MOS circuits. Now, subthreshold is important because it means the transistors are operating at extremely low voltages, almost at the very edge of turning on.
Right, for low power.
Exactly. This allows for incredibly low power consumption, making them perfect for battery-powered edge devices. Approximating complex 9-dimensional Gaussian functions, which are basically mathematical functions used to identify specific patterns in data across multiple dimensions, is achieved cleverly. They cascade simpler 1D n-type and p-type Gaussian cells in an NPNP fashion. Think of it like building a very sophisticated multi-layered filter by stacking simpler individual filters. Each tiny filter subtly shapes the incoming signal, and when combined, they can recognize highly specific and nuanced patterns in the input data with incredible energy efficiency.
Okay, stacking simple filters to get complex pattern recognition. Clever.
But here's where the design truly shines, and it circles back to that idea of leveraging imperfections. Remember those random and fixed parameters of these Gaussian hidden nodes?
Yeah, the ones that act as weights between the input and hidden layers.
Precisely. Those weights arise naturally from the inherent device mismatch and nonlinearity within the MOS transistors themselves.
So the tiny manufacturing differences between transistors actually create the random weights.
That's exactly it. It's revolutionary. In traditional designs, engineers would spend vast amounts of time and resources trying to meticulously mash every transistor to eliminate these variations. Here, they're embraced. They are the weights. This eliminates the need for storing these first-layer weights in separate power-hungry memory, dramatically saving space, power, and computational overhead.
Wow.
This subthreshold operation, combined with a minimum transistor count, results in an incredibly low area footprint and minimal power consumption, making it perfectly suited for the resource-constrained environment of edge devices. Now, to manage the flow of this process data to the subsequent Memristor crossbar array, the CMOS encoder also includes a row select encode unit and a control unit. These units intelligently time multiplex the output of the hidden nodes, synchronizing the entire process and providing precise timing pulses to ensure everything works in perfect energy-efficient harmony.
That's genuinely innovative, turning what was once considered a design flaw, that mismatch, into a fundamental strength. Okay? So once the CMOS chip has performed this intricate feature extraction and initial processing using those Gaussian cells and leveraging mismatch, it hands over the data to the Memristor chip. This Memristor decoder chip isn't just a passive storage unit, then, is it? You said it does calculations. It not only remembers, but also performs crucial calculations right where the data is. Taking us right into the heart of in-memory computing you mentioned earlier, what exactly is its role and how does it accomplish this?
You're absolutely right. It's far from passive. The Memristor decoder chip is where the true magic of in-memory computing unfolds. Its central component is the Memristor crossbar array. Imagine a grid, a mesh, of these tiny HBN memristors. Here, the output weights those critical connections between the hidden layer from the CMOS chip and the final output layer of the neural network are directly programmed into the conductance states of these memristors.
Using those 26 states you mentioned earlier.
Exactly. This is key because the array itself then performs the essential multiply and accumulate, or MSE, operations. It literally multiplies the incoming hidden node output voltage, the data from the CMOS chip, by the stored quantized weights within each memristor. And then it accumulates or sums up these results along the columns or rows.
Doing the math right there in the memory grid.
Precisely. This is the core operation of neural networks, and performing it directly within the memory array is immensely efficient. It slashes energy waste and boosts speed compared to moving data back and forth. As we discussed, these are the multi-layer HBN memristors, capable of storing up to 26 stable quantized conductance states. This multi-state capability provides the necessary precision and richness for representing those output weights effectively. Now, to manage the incoming time multiplex data from a CMOS encoder, there's a synchronized row select decode unit. This unit ensures that the outputs from the CMOS chip are routed to the correct rows of the memristor crossbar at the right moment.
Keeping everything in sync.
Critical. Finally, the system includes a sophisticated mixed signal interface unit. This unit is composed of an array of current mode log domain differential pair integrator, or DPI, circuits.
DPI circuits. Okay. What do they mean?
Think of these DPIs as tiny, highly sensitive signal collectors. They tally up the strength of each output current coming from the columns of the memristor array. As the outputs are scanned from the memristor crossbar, these DPIs accumulate the charge over time, effectively integrating the results, adding them up. The final outputs from these integrators are then compared to a predefined threshold for classification. That gives us the network's final decision, whether it's recognizing a specific sound, an image, or an activity. It's a remarkably compact and efficient decision-making engine built right into the memory structure.
That detailed breakdown really brings the mechanics to life. It's quite an elegant system. So these memristors can hold multiple states. The CMOS encoder leverages intrinsic device variations. But a critical question remains. How does the system actually learn what to remember in those memristor weights? And crucially, how does it deal with the natural variations and inherent imperfections in these brand new types of devices, the memristors themselves, ensuring consistent and reliable performance? It sounds like there must be a highly sophisticated training process at play to make this robust in the real world. You can't just hope it works, right?
Oh, absolutely not. And this is where the intelligence of the software meets the nuances of the hardware. It's a really crucial part. The network is trained off-chip before deployment, and it uses a very specific and advanced, modified, quantization-aware stochastic gradient descent (SGD) learning algorithm.
Okay, that's a mouthful. Quantization-aware SGD.
Right. It isn't just a standard learning algorithm you'd pull off the shelf. It's a bespoke solution specifically designed to account for two critical factors that arise when working with novel memristive devices and a discrete number of states.
Two factors, what are they?
First, it addresses the quantization error. Imagine you've learned a perfect, continuous, ideal weight for a connection in your neural network during training. Like the perfect strength is 0.735. But now you have to map that ideal continuous value to one of only 26 discrete, distinct states that a memristor can actually hold. Maybe the closest states represent 0.71 and 0.75.
So you have to round it off, basically.
Exactly. There will naturally be an inherent approximation, a rounding off, if you will. The quantization-aware algorithm is designed to anticipate and minimize the impact of this error during training. It essentially teaches the network to learn with these discrete steps in mind from the very beginning. It knows it only has 26 levels to work with. It's like training a painter to create a masterpiece using only a fixed palette of 26 specific colors rather than an infinite spectrum. The painter learns to work within those constraints effectively.
That makes sense. Training it to be aware of its own limitations. What's the second factor?
The second factor, and equally crucial for novel hardware, is that this algorithm explicitly accounts for the statistical variability inherent in individual Memristor devices. These aren't perfect, identical components coming off the manufacturing line. There will be device-to-device variations. One Memristor might settle slightly differently than its neighbor when programmed to the same state, and even a single device might behave slightly differently from one operational cycle to the next. There's some inherent noise or drift.
So dealing with real-world messiness.
Precisely. To achieve true robustness, the algorithm includes sophisticated parameters for the mean and variance of each of the 26 memristor states. This means the learning process isn't operating in an ideal vacuum. It proactively understands and compensates for these real-world variations during training. It learns knowing that state 15 might actually range slightly around its target value. It doesn't get caught off guard by them during actual operation. This proactive, imperfection-aware approach turns what could be serious device shortcomings into manageable, predictable parameters within the learning process itself.
So it builds the tolerance right into the learned weights.
Exactly. It's a foundational element that ensures the system remains highly robust, reliable, and effective in real-world applications, even with the inherent variability of these cutting-edge devices.
That's a truly elegant solution. Almost like the system is learning to navigate a slightly bumpy road while still reaching its destination with precision. Okay, this all sounds incredibly innovative in theory, combining these advanced materials with clever, variability-aware algorithms. But, as always, the real test of any groundbreaking technology is how it performs in the real world under various conditions. So, did this hybrid architecture actually deliver on its promise? What kind of results did the researchers see when they put it through its paces on real-time data? Did it work?
It absolutely delivered, and the results are incredibly encouraging, showcasing the system's versatility and effectiveness across a range of classification tasks on real-time datasets. Let's look at the high-dimensional data first, which is often the most challenging for edge devices. For audio classification, they perform tests on the Environmental Sound Classification, or ESC50 dataset. This includes a diverse set of real-world sounds, like animal noises, natural landscapes, human non-speech sounds, interior domestic environments, exterior urban sounds, a real mix.
Okay, complex sounds.
Yeah. They also use the Free Spoken Digit Dataset, or FSDD, for speaker recognition identifying who is speaking a number. For these, they extracted features offline using a specialized CAR-IHC cochlear model, which mimics how the human ear processes sound. It pulls out the important acoustic features. Now, the results... For example, for ESC50 animal classification, the system achieved a remarkable 90% floating accuracy and an equally impressive 89% quantized accuracy on test data.
90 and 89%, that's very close.
Extremely close. For FSCD speaker recognition, it achieved 82.25% floating and 80.00% quantized accuracy on test data. This is quite good, and again, very close. Shifting to image classification, they utilized the Semyon digit recognition dataset, basically, recognizing handwritten digits. There, they achieved 90.66% floating and 89.33% quantized accuracy on test data. These numbers demonstrate a consistently high level of performance, even with the constraints of using those quantized memristor states.
So strong performance on complex audio and images. What about simpler data?
Good question. Beyond high-dimensional data, the framework also demonstrated strong performance on lower-dimensional data sets. For these, they used a standard ELM framework without the local receptive fields part, as the input wasn't as complex. This included tasks like an activity recognition system based on multi-sensor data fusion, or AIR-IM. This dataset involves classifying activities like walking, bending, lying, and sitting based on sensor readings. For instance, classifying walking achieved 92% floating and 89% quantized test accuracy. Again, very solid.
Recognizing what someone's doing from sensors.
Yep.
Useful.
Very useful for health monitoring or context-aware devices. They also tested it on other real-time data sets, common benchmarks in machine learning, like breast cancer prediction, achieving 92% floating and 89% quantized accuracy. The ionosphere dataset reaching 89% floating and 87% quantized accuracy. And the Haberman dataset achieving 75% floating and 70% quantized test accuracy. A bit lower there, but still demonstrating capability. What truly stands out across all these diverse tests is the consistent performance and, as you noted, the surprisingly small gap between the ideal floating accuracy and the practical quantized accuracy.
That's a lot of impressive numbers across a wide array of applications, From sounds to images to activity, it
Mhm.
seems quite versatile. And you just touched on something I wanted to dig into again. They consistently report both floating accuracy and quantized
Yeah.
accuracy. What's the practical difference between those two metrics, and why is it so incredibly important that they're consistently so close in all these results? It really seems to be a key indicator of the system's success, but it's not immediately obvious what it means to everyone listening. Can you elaborate on that?
That's a critical distinction, and you've hit on a very important point about the practical viability of this system. It really tells the story. Floating accuracy represents the system's theoretical ideal performance if it were to use full precision continuous weights. Essentially, if you had an infinite palette of colors to paint with, or an infinitely precise dial for every connection strength in the neural network, it's the benchmark, the best case scenario, calculated on a computer with standard floating point numbers with perfect, unlimited precision.
The absolute ideal.
Exactly. Quantized accuracy, on the other hand, reflects the actual performance predicted when those learn ideal weights are meticulously mapped to the discrete, limited states available in the memristors. In this specific case, we're talking about mapping those ideal weights to one of those 26 stable conductance states the HBN devices offer. So it's the performance with that fixed palette of 26 colors, considering the real hardware limitations.
Okay, ideal versus the real-world hardware implementation.
Precisely. The fact that these two accuracy metrics are consistently so close, often within a mere 1 to 3 percentage points across such diverse tasks, is a profoundly critical validation of this hybrid system. It demonstrates that the network can operate with very high precision and effectiveness, even with the inherent limitations of discrete memory states. This isn't just a minor achievement, it's a significant breakthrough, especially given the natural variability and novelty of these new Memristor devices. It proves that the sophisticated quantization-aware learning algorithm we talked about,
The one that learns the limitations.
yes, that algorithm, combined with the excellent device properties of the HBN memristors, is robust enough to make this a truly viable solution for practical real-world applications, especially where precise analog control is required, but the full digital precision of traditional systems is simply too costly in terms of power or area. It basically says, look, we can get nearly ideal performance even with these real-world practical hardware constraints. That's a huge statement.
That explanation really crystallizes why that close proximity is such a big deal. It's proof it actually works well in practice, not just in theory. So bringing it all together then, what does this all mean for you, the listener? Why should this hybrid system matter to how we build the smart tech of tomorrow? And what are the overarching advantages that truly make it such a significant leap forward for efficient and powerful edge computing? For the listener thinking about the next generation of smart devices, what are the key takeaways?
Well, if we connect this to the bigger picture, these fundamental advantages translate directly into the ability to create a new generation of devices. More powerful, incredibly efficient, and highly adaptable AI-enabled edge devices, spanning everything from sophisticated smart sensors to advanced robotics and context-aware wearables, things that live out in the world with us. The source material highlights 7 key advantages that really define this breakthrough. It's worth listing them.
Okay, let's hear them.
First, and truly ingeniously, it demonstrates remarkable tolerance to device variability. As we discussed, instead of fighting against inherent imperfections, this system actively utilizes the intrinsic MOS device mismatch, those slight random differences between transistors. They become the random weights between the input and hidden nodes. This isn't a bug, it's a profound feature. It completely eliminates the need for separate power-hungry memory storage for these initial weights. It's a design philosophy shift that reduces complexity and saves power dramatically.
Turning a negative into a positive. Got it.
Second, it offers significant robustness to process variations. This means the architecture is inherently resilient. It allows for its design at much lower CMOS technology nodes than previously thought practical for this kind of analog approach. This paves the way for further improvements in system performance parameters, think even smaller, faster, and more energy-efficient chips down the line, without having to completely redesign the underlying principles.
Future-proofing, in a way.
In a way, yes. Third, and absolutely critical for edge devices, it boasts very low energy consumption. The overall energy footprint of this hybrid system is exceptionally low. To put a number on it, the CMOS power consumption per computation for a single hidden node was found to be only 7.8 microwatts at a 0.95 V supply. That's tiny.
Microwatts. Very little power.
Extremely low. This makes it an excellent, perhaps even essential candidate for resource-constrained edge computing applications where every single joule of energy counts.
Extending battery life, enabling smaller form factors.
Makes sense. Number 4. Fourth, the system offers incredible modular optimization and flexibility. Remember the electrical isolation of the CMOS encoder and Memristor decoder chips? That's a brilliant design choice. It means each part can be optimized separately without needing to re-engineer the entire system if you want to improve just one part. Even more compellingly, it means that as other emerging memory technologies, maybe even more advanced phase-change memory or different types of RAM mature, they can potentially be explored and integrated simply by replacing the decoder chip, without affecting the existing validated CMOS encoder. This future-proofs the design significantly and accelerates innovation.
Swap and play memory.
Nice. Fifth, the Memristor array performs efficient multiply and accumulate MSE operations. These are the fundamental arithmetic workhorses of neural network processing, as we said. By executing these directly within the memory array, the system can handle higher dimensional input feature maps and stored quantized weights incredibly effectively, drastically reducing the von Neumann bottleneck that plagues traditional systems.
Faster calculations, less data movement.
Exactly. Sixth, the 9D Gaussian CMOS circuit, by operating in the sub-threshold regime with minimal transistor count, provides the desired nonlinearity while maintaining a low area and low power footprint for the encoder chip. This compactness and efficiency are paramount for integrating complex AI into tiny, distributed devices. You need small and efficient.
Absolutely. And the last one.
And finally, seventh, the framework offers a powerful digital memory substitute with its multi-state memoristive device. This means it can replace chunks of traditional digital memory, leading to significant savings in both energy consumption and physical area footprint compared to conventional designs that need separate memory blocks. In essence, these 7 advantages collectively pave a clear pathway. A pathway to a new generation of smarter, more efficient, and incredibly powerful AI-enabled edge devices that truly understand and react to the world around them in real time.
Those are profound advantages, painting a very clear picture of why this hybrid approach is so vital for the next generation of computing. Really compelling stuff. But building something, this cutting edge, involves pushing the boundaries not just of theoretical design, but of actual manufacturing.
Right. We're talking about new materials, these 2D sheets, and innovative ways of integrating them. What can you tell us about how these memristors are actually made and integrated into a system like this? How do you reliably produce these tiny multi-state devices at a scale that matters? It sounds incredibly delicate.
That's an excellent and crucial question because a brilliant concept is only as good as its manufacturability. You have to be able to build it reliably and affordably. The fabrication process for these HBN Memristor crossbar arrays is meticulously managed, but it employs a scalable 3-step method using pretty standard semiconductor techniques. First, the foundational wiring. Gold or OGU bottom electrodes are patterned using standard photolithography and e-beam evaporation onto a silicon dioxide desilicon substrate. Basic stuff. This creates the precise electrical pathways upon which the memory elements will sit. Okay, laying down the wires first.
Exactly. Second, and this is where the advanced 2D material takes center stage. Approximately 6 nanometer thick CVD HBN sheets grown separately on a copper substrate are carefully transferred onto these bottom electrodes. This is done using a standard wet transfer method involving chemicals like FeCl3 and PMMA. It sounds complex, but it's a relatively standard procedure in materials science labs now. This delicate yet scalable process precisely positions the HBN as the crucial dielectric layer, the material that actually changes its resistance between the electrodes.
So you grow the HBN elsewhere and then move it onto the chip.
That's right, using CVD growth, which is scalable. Then you transfer it. It's like building with atomic level precision, but using techniques that can potentially be scaled up for manufacturing. Third, another matrix of O-top electrodes is patterned and deposited. These are then precisely aligned over the HBN and the bottom electrodes to form cross-point junctions. These junctions define the active area of each individual memristor. For the devices tested in this study, these junctions were typically 5 micrometers by 5 micrometers.
5 by 5 microns. Still pretty small.
Very small.
Yeah.
But what's particularly promising for the future is that the research also demonstrated the potential for much greater miniaturization. They showed viable 150 nanometer by 200 nanometer cross-point devices, and even nanodot devices with a radius of approximately 25 nanometers,
Much, much smaller.
orders of magnitude smaller. This indicates excellent potential for achieving incredibly high integration density in future designs, packing even more intelligence into smaller spaces. But what's absolutely critical to highlight throughout this discussion of fabrication is that only scalable methods were used. For both the material growth, CVD, and the device patterning, photolithography, standard deposition, this is essential for facilitating their integration into existing semiconductor fabrication lines, or fabs. It means these aren't just one-off lab curiosities, they are designed with industrial production in mind.
That's a huge point. Designed for manufacturing.
Yes. And on the CMOS side, just to complete the picture, the encoder chip design itself was done using a mature, well-understood 180 nanometer technology node, and its performance was extensively verified through rigorous post-layout simulations, ensuring its compatibility and robust operation when integrated with the Memristor array.
That detail about the manufacturing process and the scalability is incredibly important. It shows that this isn't just a theoretical breakthrough, but one with real-world potential, maybe sooner than we think. This hybrid framework seems incredibly forward-thinking, especially with its modularity and its ability to leverage imperfections. How adaptable is it for future developments, and what wider impact could it have beyond just these specific audio and image classification applications we've discussed? It truly feels like it's laying foundational groundwork for much more to come.
Indeed, the modularity is one of its most powerful and strategic features, I think. That electrical isolation between the CMOS encoder and Memristor decoder chips fundamentally provides an unparalleled degree of flexibility. Flexibility for future exploration of other emerging memory technologies. This raises an important question, right? If a new, even more efficient type of phase change memory comes along, or a different ARM material with even better properties, or some other exotic memory solution we haven't even thought of yet,
Uh-huh.
this system can potentially integrate it simply by swapping out the decoder chip. You wouldn't necessarily have to redesign the entire CMOS encoder from scratch, which is a massive, expensive undertaking.
So you keep the smart front end and upgrade the memory processor part.
Exactly. This significantly de-risks future development. It allows for rapid iteration and opens doors to integrating even more advanced memory solutions as they emerge, accelerating the overall pace of innovation in edge AI. It's a truly adaptable platform.
Very smart design.
Ultimately, the design system is generic enough and its principles are fundamental enough that it can be applied to a remarkably wide range of applications, beyond those specifically tested in the paper. Think about enhanced audio detection for smart homes, recognizing specific sounds like glass breaking or a baby crying. Highly accurate speech and non-speech detection for virtual assistants. Nuanced image classification for autonomous vehicles, maybe identifying vulnerable road users under difficult conditions, and countless other edge computing tasks. Tasks where constraints on latency, power, and physical area are severe and non-negotiable. It effectively overcomes the area wall and the memory wall challenges often faced in traditional CMOS designs by leveraging this near-memory, in-memory computing approach with these innovative 2D memristors. It's not just an improvement, it's potentially a foundational step towards highly efficient, intelligent, and truly adaptable edge devices that will power the next generation of our connected world.
We've just taken a deep dive into a truly fascinating intersection of old and new, integrating the reliable, well-understood workhorse of CMOS technology with the cutting-edge capabilities of 2D material memristors. It's a powerful reminder, I think, that sometimes the most impactful solutions to our biggest technological challenges come not from abandoning the past entirely, but from unexpected combinations and a willingness to rethink fundamental design principles, even those that seem immutable, like device mismatch is always bad.
And that leads us to a truly provocative thought to consider, doesn't it? If a system can not only tolerate but actively leverage inherent device imperfections, like the mismatch and nonlinearity we discussed, to its distinct advantage, what other fundamental design principles in engineering and technology might we need to reconsider? Could embracing imperfection and intentionally designing with variability in mind, rather than constantly fighting against it, be the key to unlocking the next wave of innovation? Not just in computing, perhaps, but across many other fields where we traditionally strive for absolute uniformity and perfection.
A truly profound and thought-provoking idea to leave you with. Could embracing imperfection be the future? Something to ponder, and one that could fundamentally reshape how we think about building the future of computing and beyond.